This video is my submission to 2022's Summer of Math Exposition, second year in a row, SOME2. I will be presenting an original mathematical discovery that you will not find on the books, and I call it God's Binomial Identity. Not just because it's deep and profound and nearly universal and amazing and useful, but because a mathematician must always cite their sources, mustn't they? The theorem behind it all takes a product of however many factors and transforms it into a sum of signed binomial coefficients. If nothing else, this video will teach you how to perform the greatest mental math trick you've ever seen. It will make you fun at parties. Well, at math parties anyway. Friends, colleagues, students, professors, whoever will be stunned and amazed. And here's what it looks like. You say, give me a number. And then let's just say, for example, they say, okay, 33. And then you say, and you consult the ether, and then you start channeling. 22, choose 19, plus 8, choose 3, plus 18, choose 15, plus 10, choose 7, minus 21, choose 18, minus 19, choose 3, minus 11, choose 8, minus 7, choose 4. And then you say, okay, now sum up those binomials. They might need a little time, pen and paper or computer or phone, to actually even just evaluate the binomial coefficients and sum them, which all adds to the amazement factor. And in this case, they're going to find this is 1540 plus 56 plus 816 plus 120 minus 1330 minus 969 minus 165 minus 35. Now you do a running sum. Starting with the first term, it's just 1540 again. Plus 56 is going to give us 1596. Plus 816 is going to give us 2412. Plus 120 is going to give us 2532. Minus 1330 gives us 1202, minus 969 gives us 233, minus 165 gives us 68, and finally minus 35 gives us 33. Bum, bum, bum. And maybe they say, oh, clearly you just lucked out. And you say, well, give me another number. And they say 110. And then you say, home and a home and a home.
21 choose 18 plus 5 choose 2, plus 8 choose 3, plus 14 choose 11, minus 16 choose 3, minus 19 choose 16, minus 10 choose 7, minus 3 choose 0.
And once again, we evaluate our binomial coefficients, and we get 1330.
Plus 10, plus 56, plus 364, minus 560, minus 969, minus 120, minus 1.
And now we'll do our running sum again. And finally, minus 1 gives us 110, our original number. Oh. And then suppose they say, well, 33 and 110 are composite numbers. I bet you couldn't do it with a prime number. And you say, okay, give me a prime number. Let's have it. Any prime number you please. And they say 11. And you say, I'm going to take it easy on you this time, buddy. We'll give you fewer terms. How's that? And you tell them, finally minus 1035 is 11. Ha ha ha. And then they say, ah, ha ha ha, yourself. I'm figuring this out. See, I give you a prime number and it's fewer terms, right? To which you reply, au contraire. You want more terms? I'll give you more terms. Here. Minus 56 is 11. There. And by this point, they will be begging you to show them how it's done, even though they're not worthy. But really, all who seek are worthy to find, so you then have to show them, because that's how it works. Before stating the theorem, I'm going to cover some background material. But if you enjoy a challenge, you could stop the video here for an hour, a couple hours, a day, whatever, and try to derive and prove to yourself what I'm about to show you and figure out for yourself what's going on, which is absolutely the best way to learn anything, rather than sitting around waiting to be taught, is to learn it yourself. All right then, no going back now. Let's take any x, and it could be a number, it could be a polynomial, it could be a Q-series, it could be the product side of an Euler identity. It could be anything that can be expressed as a product of d factors. Then this transform will transform not the number, because the x stays the same. It is the conserved quantity, but not just quantity, but quality of the thing is preserved as well, in a sense. The transform is transforming from a product to a sum of binomial coefficients. So a partition of binomials, a binomial coefficient partition that sums to x. And I'll be working on this little example on the right hand column. You see 105 equals 3 times 5 times 7. So we say that that is a degree 3 product, has 3 factors. And this transform will then transforms it into 2 to the 3, aka 8 signed binomial coefficients that sum also to the quantity x, or the thing x. So notice that the first binomial that we have here is the largest one, 15. Choose 3, and note that the 15 simply comes from the sum of the factors. 3 plus 5 plus 7 gives us that 15. Now move on to the second grouping. Then we call that the K4 in this case. Because there are 4 groupings. The next one, so that first one is basically the sum of the elements of the D subset, aka within K subsets, the 3 subset is the subset of the power set containing 3, 5, and 7 as elements, so the sum of them is 15. So the upper part of these binomials are all the sum of the elements of the subsets within the power set of the product factors considered as a set, or in this case a multiset, because multiplicities don't matter, and they're taken care of automatically, and so it's kind of universal that way. We don't need to worry about making the distinction, and we can deal with multisets. Alright, so let's take a look at this second grouping of binomials. So these are going to be, because we're going from 3 to 2 to 1 to 0, these are the 2 subsets. So 12, the 12 in 12 choose 3 comes from 7 plus 5. The 10 comes from 7 plus 3, and the 8 comes from 5 plus 3. Then we move to the next grouping, the 1 subsets. How many subsets are they that have one element? There's 3 of them, and they are 7, 5, and 3. And we just put a 3 underneath for the bottom, which is always the degree of the factorization, or the number of factors in the product. So, when you're doing that challenge at the beginning, because n choose k equals n choose n minus k, you can on the fly change things up a little bit to add a little more confusion, and just subtract the lower from the upper and use that difference as the new lower. So 12, maybe when you're doing this in your mind and you're channeling these binomial coefficients, instead of saying 12, 3, you say 12, and you think to yourself minus 3 is 9, and you say 12, choose 9. And then maybe for the 8, 3, you say 8, choose 5 instead of 8, choose 3, just to make things a little spicier. But as you notice, there they are. And look at the quantities of the subsets, of course. That 1, 3, 3, 1. These are the polynomial expansion of x plus 1 to the power 3. So there's one 3 subset, there's 3 2 subsets, there's 3 1 subsets, and there's 1 0 subset, which corresponds to the empty set. So our multiset is this capital F containing d factors. And anything, if you go into just rational numbers or even real numbers, rather than restricting yourself to integers, you can have as many factors as you want, willy-nilly. You just make them up. So considering integers, of course, here where the possibilities are limited, because it's going to come down to, if you're looking at a number x, how many ways can it be uniquely expressed as a product of however many factors. Truth be told, because of the universality of this identity, you can include additional factors of 1 as many times as you want to raise the degree of the product, and thus the number of binomials in your binomial sum set. So and that's it. The upper arguments of the binomials in the transform are the sum of the elements of each of the subsets in the power set. So here we're going to call those EI for elements, and I is the first element, second element, and there, if it's a k subset, there's going to be k elements in it. So EI as I goes from 1 to k of the elements in the k subset, and it's the jth k subset, because like just an example on the right, the 2 subsets, there's 3 of them, so we need j equals 1, 2, 3 to get those, to catch all of them. And the 3, of course, is just d choose d minus k. You could say d choose k also. I'd like to start with the the d subset, because that always ends up being positive. If you look at the last one, it's the corresponding to the empty set. It is I wrote that as delta choose 3 here, and of course it's 0 because delta is 0. That's the base case. That's the default. But using a delta, a variable delta rather than an empty set, because nothing stops us from assigning value to that delta eventually. But we got to cover some more basic ground first. So we're just dealing with the base cases here, and as you see here now, continuing, we're in pink and green here. The sum of the factors is the same as the sum of the EI in the D subset, the first D subset, which is the only D subset. So FI and EI are the same, the initial set, and then you can enumerate the subsets in their grouping, add those factors to every way that you can add 2 factors, every way that you can add 1 factor, and use those to form the upper arguments of your binomial coefficients. The sign is easy, it's -1 to the k, so they alternate for each of the k groupings, and there's always d plus 1 of these k subset groupings. Alrighty, so that's it. But what it does from here, what it means, well, I mean, means that wherever you have a product in any of thing you're doing, you can now just plunk in this transform, and you're going to be able to examine your theory, your research, your formula, your algorithm, whatever you have, and you're going to be able to split it up and into these varying sized partitions of binomial coefficients, and then be able to do things with that x that you couldn't do just dealing with the product alone, or other sets that sum to them, such as the regular partitions of x, for example. Okay, let's do a quick review in terms of a cubic or third degree product in general, a times b times c. And for clarity, and you can stop and pause the video if you want to examine this, let's write out each of these elements in terms of this notation, this EI. Just break it down, each of the, here right now on screen, put the I numbers in there of the element counting, and the J's running across the top, which is within each grouping, and of course there are D plus 1, or in this case 4 groupings, ending with the last one there, which is the empty set. And I'm about to write E 0, 0 comma 0. That should actually be 0 comma 1, because there is one element as far as the way that we're counting. So and then we can use a little notation to indicate that sum of elements of the jth k subset for the given D. Of course, so if D is obvious, then you can skip that, and we can just express that sum as skj. And using that, we can restate our theorem this way, where if D is obvious, then we can just leave it out and use skj as we've done here. All right, so we have this, which is the same as what I just wrote, except I'm using SD minus KJ instead of SDJ. It gives you the same thing, it just makes the ordering descending by magnitude. Before moving on to proof, let's just do another example with 4 factors here. I end up using this D star, so it's not confused with degree. But I'm basically writing out the same stuff I just wrote out before for a cubic example. And you can stop and pause and ponder that and look back, and I'm sure that it will be clicking with you if it has not already. And of course, the thing to notice here is that the signed groupings of binomials are grouped by the 4th degree coefficients in a power expansion, 1, 4, 6, 4, 1. And also note, and I'll state here, that this is the delta equals 0 is always the base case. So this is always our reference, is this delta equals 0. Okay, let's prove the identity. And this is interesting because it's both a constructive and an inductive proof simultaneously, if that makes any sense. And it doesn't. So how can you say something like that? And I'm like, well, that's what it looks like. All right. So anyway, so let's take our factor set. Let's take the case that our factor set is a single element, x. Now the transform tells us that with one factor in our factor set, we should end up with 2 signed binomial coefficients in our sum set. That's what we should get. And we do. They are x choose 1 minus delta choose 1. So now let's take another number y, and we will multiply x and y together on the binomial sum side of the formula. Now I mentioned this before about the delta variable, but maybe it got cut in editing, but because the timing wasn't right. But essentially what needs to be pointed out is that delta, the empty set, again, it is everywhere. It's attached to everything. So we put it on at the end, but it's here all along in every term. X plus delta x, y plus delta y, or just even a delta x or a delta y by itself. But always there. And if we were to subtract the d on the bottom from each of these terms, the bottoms would be x plus delta x minus 1, y plus delta y minus 1. And then that's the form that we would want to use these in for it just makes things a lot easier for some of the things that we're going to do. So you use whatever works best and easiest to see in whatever situation you're in. So this expansion is just like any other product expansion of sums of terms. And in this case, if we multiply the binomials together, then we get x times y minus 0 minus 0 minus 0. It's not really that earth-shattering. In fact, it is not at all what our theorem says that this thing should look like. If we use our theorem to come up with a binomial set and do not multiply those out that way, then this is what we get. Compare this to what we just had for x times y. Obviously, the two middle terms of what we have in red there are not going to be equal to 0 for almost all instances of x and y. But here is where something stunning happens. So stunning, I call it the miracle property, which is perfectly in line with the theme of God's binomial identity. And if I take that naive expression of x times y, the one in black, and for the pairs of binomials that are multiplied by each other, instead of multiplying them by each other, what I'm going to do is we're going to add the upper arguments and the lower arguments and use those as the upper and lower arguments of a new binomial. So as you can see, this produces x plus delta x plus y plus delta y over choose 1 plus 1. And if we just simply say delta star is basically a reformulation of delta x plus delta y, and then write that in like that, well, first of all, you're going to notice that there is a delta x plus delta y in the upper argument of every binomial. So this is legit. So no matter what values we assign to delta x and delta y, our delta star will still have a that'll just determine what the delta star value is. So we can write out the expression like this and look at that expression compared to the expression at the top of the page. It's the exact same expression. And as I said, though, there's a certain utility in using the alternate form. This form here where you have that 2 across the bottom, it's very nice for making it super clear that you're dealing with second degree binomials, and which are all on the same values given by the same polynomial. Then we can take this expression that we have here and we can multiply it by a third number, z plus delta z, choose 1, minus delta z, choose 1. And we're going to end up with this expression. Actually, let me start on a fresh page for this one. Now let's write out our transform. First, we'll define delta 3 for 3 factors, to be the sum of delta z plus delta star from the previous from the start of this example. Our theorem tells us that the product of x times y times z is this expression here. And we've done an induction on the theorem's predictions. And also we've seen that we can construct these expressions directly from the ground up, starting with the first factor and build it factor by factor, multiplying them in whatever order you please to get the equivalent expression. But this relies on using the miracle property. And is that true? Should it be true? Why does it work? in a nutshell, you have this product universe and this sum universe of binomials, and what happens in one happens in the other. They just look different depending on which one you're in and which one you're looking at. And we can demonstrate that the miracle property uh, must be true, and that's what's going on the screen right now. In green there, we're starting with a degree 1 number, some x, and then converting the two binomials into their ratio of factorial form. And we get x, and then we're doing the quadratic, and we end up with exactly what we'd expect, that indeed does equal xy. And we can keep going on up and stuff like that. So there's more induction going on under construction. Induction under construction. But essentially it comes down to something very simple, I think, which is that in the lower arguments of the binomials, adding those together is bumping up the degree, and adding the upper arguments of the binomials together as you go from degree to higher degree to higher degree, you are building the power set. and it's sort of like the whole shebang is following a Pascal's triangle-like recurrence. Let's look now at what happens when delta takes on values other than 0. Here, just using an example, for 2 times 3 times 5, we write out the binomial sum set, and then that's the third degree binomials. Then we convert them by subtracting the 3 from the upper argument to work with, and we evaluate them here, and we got that 120, 56, 35, etc., etc. If we do the running sum, we see that they do indeed add up to 30. All right, now let's start with the delta equals 0 base case, which is what we just wrote. But let's rewrite it here so we can put some stuff on either side of it, and see what we got. So when all of your binomials are this form that has a delta in the upper and lower arguments, it becomes a simple matter of adding the delta adding delta to both upper and lower. So here the leading coefficient, or the leading binomial, was 10 choose 7, 120. So we just know that for delta equals 1, we get 11, 8, and then 9 choose 6, and etc. like that. And so we're just taking actually the next binomial in the polynomial sequence that describes the cubic binomials: 1, 4, 10, 20, 35, etc. Once we have that delta equals 0 base case, we don't need the formula anymore. We can just write it out, and then just notice that every column is the same sequence from the cubic polynomial that describes the choose 3 binomials. It's just a matter of what is the offset. And as we add or subtract delta, we're just going one at a time. For 1 unit of delta, we're moving to the next set of binomials. And so we get this wonderful expression that is equivalent to x everywhere. You can put in real deltas, you can put in complex deltas, you could put in a function for delta, and it is always going to preserve and conserve that x thing on the left side of the equation. So this is like a perfect conservation law. And now let's notice something really, really interesting. And the reason for ordering the binomials as descending within each of their k groups. There must always be a value of delta that gives a symmetric expression of the binomial sum set. And in this case here, that delta is -4. And we see that we have this line here where we go 20, -4, -1, 0, and then obeying the signs on the right, 0, 1, 4, 20. The sign changes always work out, and with the specific ordering, the value of delta that gives this symmetric expression is always going to be the one that gives you the first and last coefficients equal, or any the first and the first from the last. Here's an example for 2 times 5, and showing us that the delta sim, the delta for the symmetric case, is going to be given by -3 here. Here we do an example with an odd x and 2 degrees, or a quadratic case, for which we're going to find that our delta sim is a half integer value, and in this case -3.5. And the sum set at delta sim in this case will have half integers for all the upper arguments, perfectly valid, where it is straightforward to prove to oneself that the outer binomials in this case are equivalent. Plus 4.5 choose 2 and plus the binomial -3.5 choose 2 are equivalent. And the same for the 2 in the middle. It's also very straightforward to derive the formula for delta sim, here going back to the 2 times 5 case and working it out. Delta sim is the sum of all the factors plus 1 minus d, the degree, over 2, and then that whole thing multiplied by -1. So we can state a formula for delta sim just like this, and then we can go back to any other example and apply it. Here, let's take that and apply it to the x equals 3 times 5 case, and of course we do derive our -3.5 as delta sim. For those familiar with fast Fourier transforms, you may have noticed that going to the symmetry line is very much like that in terms of moving to the center to be able to reduce the computational load. Only this is the sum analog of that, and if anything, we're saving on memory space as opposed to processing time. Also, the identity gives us new methods to examine problems involving sums of powers and such, like Fermat's last theorem, and also Beal's conjecture, but also the ABC conjecture, not powers, but just basically factorizations in general. Another area where this seems to give immediate deep insight is into automorphic forms. Think about that grid of the changing delta values. When we change delta by a unit step and we're conserved on the left and still have integral values for binomials on the right, that is a sort of essentially what we're doing with an automorphic form when we take one step and then we get the same value back, more or less. This, combined with being able to deal with polynomials in the same way, kind of, well, let's just say I wouldn't be surprised if some major issues in the Langlands program get laid bare in short order by examining what's going on in light of this identity. But let's get caught up with what's going on the screen. I started with an expression of Fermat's last theorem and just mentioned that you could take the 3 terms in the equation and do a transform where we do a simple factorization of n factors, and we can do something similar with Beal's conjecture. But with Beal's, what we can do is multiply the of the x, y, and z exponents, one of them or maybe 2 of them are going to be a maximum. So we can just multiply 1 to m minus x times ax, etc., so that we're bumping up the degree of each of those terms, and then work the problem on these symmetry lines to see what that gets us. Let's look at some more examples with this gizmo and with a focus on pure powers in the symmetry line of the pure powers. Here in the brackets on the left are the, in this case, quadratic case, the 2 factors followed by their product, and then that next number is the delta value, and the final number in that first set is the symmetry, is delta symmetry. and then we see what we get on the right with the top line being the KJ index, and then followed by the binomial representation unevaluated, and then the evaluated binomials, and then the running sum underneath. So here for 7, 7, right now we're at 0, so we see this 91, negative 21, negative 21, 0, so definitely not symmetrical. So let's move delta to the delta sim, negative 6.5 in this case. And notice that the inner pair values are each 1/8, a positive 1/8, meaning that binomial 0.5 choose 2 evaluates to a negative number. But the polynomial for choose 2 binomials is positive going to plus infinity and positive going to negative infinity. So obviously we are between zeros here. Between the zeros of that one small span where the sign flips. Also notice that when we're dealing with the integer product of 2 factors, that this 1/8 denominator is persistent. It's everywhere, including when our factors are 0 and 0. In which case it's also interesting that no matter what delta is, we still get a symmetrical expression when the factors are all 0, regardless of which value we use for delta. It's kind of like the delta sim of the empty set. Here's the delta sim line for 1 times 1, and here it is for 2 times 2, and here we have it for 8 times 8. For quadratics on the symmetry line, the central pair values are always 1/8, and the delta sim is always the negative of the base plus 1/2. Now let's look at cubes. For 7 cubed, we have a common denominator of 16 now instead of 8, and the 6 inner terms out of 8 are all identical, and quite a bit smaller than the outer pair of binomials. And in general, for higher powers, this distribution of binomial values, regardless of sign, thinking in terms of magnitude only, will always follow this bathtub curve, being hollowed out in the middle and all the action taking place on the edges. Roughly, of course. The point being is that only for the quadratic case might we have this kind of thing where all the middle terms are positive and constant, of a constant value, which might be the thing we need to distinguish the Pythagorean triple case from all other combinations of powers. For the cubic with an even base, we're always going to get integers for the distribution on the symmetry line, but we could multiply those by 16 and list them out with the values on the odd to sort of normalize the numerator-denominator situation, and we'll find that these numbers follow a sensible cubic polynomial in the columns as we vary the value of delta. And just like a function morphs the number line, these delta sim distributions form a morph of the polynomials of the binomials. For Fermat's last theorem, the x to the n plus y to the n, the bases x and y, one must be even and one must be odd. So those middle terms are going to add to basically an integer value plus 6 times a 16th value. And that cannot add up to an integer when the outer pair of binomials is added into the mix, which we know because Fermat's last theorem has been proven. So if there's a proof method using these techniques for Fermat's last theorem, then it should be directly applicable to the Beal conjecture. So it is worth chasing, particularly because there's $1 million prize attached to Beal's conjecture. Not to mention applications to the other Millennium Prize problems. And it all may simply boil down to the fact that the sum of these inner pairs of terms is always negative for powers greater than 2, and positive only in the quadratic case where we get Pythagorean triples. And problems of this type are dominated by the outer pair of binomials, and there's just not enough water inside the bathtub to make any difference. On screen now is the delta sim distribution for 7 to the 4th power, and the values of the binomials within their k groupings are identical to each other. And of course the k grouping and the n minus k groupings are also are identical to each other, mirror symmetry. So this gizmo that I'm using here on the screen could be expressed more succinctly if we were dealing with powers alone, just by putting in the coefficients 1, 4, 6, 4, 1 in the 4th power case. But this one here allows us then to examine the distribution for composites on their symmetry line. Here is an example where we have 5 times 7, 35, only multiplied by 1 squared to bump up the degree to 4th power, so representing a quadratic with a 4th power expression. Here we have 5 to the 4th power as we head to the delta sim line. And of course the thing to notice on these 4th powers is that this common power of 2 denominator is 128, or 2 to the 7th in this case. And here is 2 to the 5th, where we can see that this distribution of magnitudes into a bathtub curve is persistent for integer powers only. You start doing composites of various forms and all bets are off. Well, actually that's not quite true, because we always on the delta sim line are going to have a symmetrical expression that is inwardly bimodal. It's not a bimodal distribution, but it is like that, moving inward instead of outward in terms of magnitudes, where we ignore the signs. Here we have the 5th degree product of 11 primorial, the product of the first 5 primes. And here this is for delta equals 0, and we can see that the delta sim is equal to -12. If a 5th degree product is even, we're always going to get integers in the distribution, and if it's odd, then we're going to get integers half the time. So here's an example where just to show that the denominator in this case is 256, so 2 to the 8th, and so there's not a simple arithmetic progression that the exponent of the power of 2 serving as the denominator. It goes from 8 to 16 to 128, then to 256. So it's not a simple arithmetic progression. And I conjecture that determining what that denominator will be for any given degree depends on how many powers of 2 are below d. But let's now look at some other examples of potential applications for God's binomial identity. We can apply it, of course, to polynomials. Say we have the cubic polynomial, x minus 1 times x minus 2 times x minus 3. We can still calculate a delta sim, but it's going to be dependent on x. So for this one, we get a delta sim which is negative 3x minus 8 over 2. And so we know, and we can see that when x equals 0, we're going to get a delta sim that equals 4. And then we can also ask, well, what x will give us the delta sim equals 0 case, which sounds really special, right? And in this case, it's 8 over 3. But the point I want to make here is that we get this as our base case, and then if we add our delta symmetry, then we end up with this. And the ordering is off because of the differences and stuff, but we still have the symmetry. It's here. It's just a matter of ordering that changes. Here we have 2 instances of this one plus, 1 minus. Here we have 2 instances of this one plus, 1 minus. Here we have 2 instances of 3 halves, choose negative 3 halves, 1 plus, 1 minus, and similarly for the last pair of 1 half, choose negative 5 halves with a minus and a plus. So this thing, boop, obviously, is 0. And that is because our x equals 1 in this case. When x equals 1, our symmetry is 3 minus 8, which is negative 5. So over 2 is negative 2.5, and then negated is 2.5, 5 over 2. And so that's what we've done here, is we've taken the x equals 1 case. Our symmetry is specific to that x, and it's 5 halves, and then we go to it, and that's where we get our symmetry. Let's look at another example. One really simple thing we can do, maybe introduce binomials and this theorem and related items earlier in a syllabus, or would be to take your multiplication table. That's what we've done here with delta equals 0. We have the multiplication table itself, x times y, and then we just break that up into the sum of 4 parts. The x plus y binomials, x binomials, and the y choose 2 binomials, and of course that's the delta. And when we sum those up, then we get our multiplication table back. But more than that, we can assign, various deltas, and we get numbers here in these matrices. But no matter what that value of delta is, when we sum them up, we're always going to recover the multiplication table here. Very cool. Another fun application is to imagine a sequence of the say choose 3 or choose 2 binomials, whatever you want, as a partial around the zeros, and so you put them on wheels and then make a slot machine, and you pull the lever, and these 8 or 16 or 4, however many wheels you have in your expression, each one lands on a binomial. And if that expression corresponds to a valid integer factorization, then it's a winner. And did some experiments with that, and across the board it confirms that it is a good slot machine design in terms of a slot machine, because you never win, or it's hard to win. But the numbers are quite smooth, and we're starting to enter into kind of a way to gauge out of a general or random distribution among binomials of the same degree with the signs, that is it going to be a valid composition in terms of an integer factorization partition. See, the thing that I don't think I mentioned this, but the miracle property, where you can have these expressions and then add the upper and lower arguments to create an equivalent expression of the product in terms of just working on the sum side. It means you don't have to evaluate the actual product or the actual binomials until you're done working on the sum side. Then you can evaluate your binomials and do the heavy computation. But of course, the real raw power of God's binomial identity is going to be most pronounced in the in signal processing, image processing, sound processing, music, encryption, artificial intelligence, general computing, quantum computing. It's because literally, and in physics, because whatever we have for our x on the left side, it stays perfectly conserved no matter what we do on the right side. And by that I mean by playing with this delta. So here, a very simple example is we're going to make delta the sine function. And then we're going to look at our binomial sum set, and each of those become a function as the delta runs over its function. And so we effectively take that one signal and split it into 8 signals in this case. And the sum of all of these signals will return the whatever we had on the left. And in this case, 3 times 5 times 7, simple product, number 105. But the thing on the left, it just has to be however many factors. It could be 3 wave functions multiplied together to create a master wave function, and then on the right side we get 4 or 8 or 16 or 32 wave functions, because delta is assigned to be another wave function altogether. Just the possibilities are astounding. And you know, even to the point where you think, if aliens are out there and they're sending signals and stuff like that, maybe they're using something along these lines, and that's why we can't detect it, because we detect them because we've never broken things up this way, you know. And by doing so, we're going to discover sound filters, image filters, new techniques, all kinds of things. So there's a lot of low-hanging fruit in terms of intellectual property here. So yes, I have registered some copyrights on some of the basic algorithms, and means and methods and provisional patents. I want to get a workshop going, and I want to secure low-hanging intellectual property to be owned by a charitable organization that it represents the humans of the earth. So a way for the humans to own royalties and licensing to support this charitable organization, which will be focused on, for participating members, providing what we all have in common and what we all need, our core human needs. We need food, shelter, clean water, sanitation, safety, the things that we have inalienable rights to provide for ourselves. We're going to provide those for ourselves. How do we evolve the human race? You know what I'm saying? And that's what this should be all about. So I want to protect this intellectual property, not out of any sense of myself. All I really want and need is to be able to just do this, research math and physics all day long, and have people in a tribe around me where we're working on those same things together. To me, this discovery portends amazing science fiction like technologies. Another example is human consciousness in the mind itself. Brainwaves are notably come in 8 flavors, and can those 8 flavors be rendered sensibly to give a 3-factor brainwave function on the left of the equation? You know, these are very intriguing questions. I'm optimistic, that's for sure, but I'm just trying to be cautious and take the steps so that mankind doesn't get rolled by a greedy few. Maybe I'm right, maybe I'm wrong, but I took the precautions. If you see the potential for this and you want to work on this and you want to do something with this, just join and work with the charitable organization, and now everybody's working together in an open, transparent way. And I guess what I could say is support my research, support a workshop, support an effort to really put this stuff through the ringer, for the sake and benefit purely of the advancement of math, physics, the sciences, mankind, etc., etc., and leave the greed monster out back in the shed for now. You know, money will ultimately take care of itself. And I also will just mention that Kurt Jamal from the Theories of Everything YouTube channel has just announced another project that is based on, and the same kind of project as Summer of Math Exposition. On his is on physics and theories of everything. I'm going to be submitting a video. I would really love to have some expertise and some coding talent to really do it justice. But I guess all I will say to that is, to a certain degree, with this one here, God's binomial identity, it looks like I've let the cat out of the bag, but really it's a kitten. There's a broader research program. There are a lot of kittens in the bag, and there's a mama cat in the bag. And with my submission to Kurt's project, I'm gonna show you the mama cat. If I have to do it all by myself with these meager skills and resources that I have, the resulting video will probably be 8 hours long or something like that. But that's all I want to do, is I just want to work with people on this stuff here. And so I hope that somebody out there gets me and understands what I'm talking about. Let's get something going. My intentions are for the best for everybody, for all of the equal human souls of the earth. Thank you.